Welcome viewers, this is Mr. Udingo again, and today we want to learn about area approximation. And before I begin the lesson of today, I would appreciate that you support us by subscribing to our channel so that we are able to continue providing you these important lessons. On the board I've written here the chapter area approximation, which is a very important chapter. Last time we talked about differentiation. So today we want to look at area approximation. Now, to approximate is simply to estimate. It means these methods we are going to, this chapter, we are not going to learn how to get the exact area of a given region, but we are going to look at an estimate, or we are going to estimate the areas, meaning the areas we are going to get with the methods we are going to explain here today could be either higher or lower based on the shape of the diagram and also the method that you use. Now in Form 1, you are taught how to estimate area, but area enclosed by irregular shapes. When you are talking about area of shapes, you looked at area of regular shapes like area of a circle, area of different shapes. But you also talked about how to estimate area of irregular shapes, and you only looked at one technique called the counting technique. So in the counting technique, we are not going to deal with it here because it's something you have learned before. So just to briefly describe the counting technique is that if you have a shape, assuming this is the region of the land that we want to determine its area, then the first thing is that we have to ensure we put a grade on this particular area. And if I sketch grades, these ones are not drawn to scale, but you can try to get one that are actually drawn to scale. Assuming these are grades enclosing this particular region here, and assuming that these boxes represent squares, so they are equal squares. Now, usually you can be told the scale of this particular region. For example, sometimes you are told the scale of this land was 1 to 5,000. 1 to 5,000 meaning that the scale on paper, 1 centimeter on paper is the same as 5,000 centimeters in the actual piece of land. So knowing that scale, we put it aside, but we come here first. We know that these boxes will obviously represent 1 centimeter. So if this box, this is 1 centimeter, this is 1 centimeter, this is 1 centimeter, the first thing we need to do here is to be able to identify complete squares. So if I identify the complete squares, I'll use ticks to identify complete squares. This is kind of not very complete, but I'll take it because we are estimating. So I'll try to use my judgment to decide which one is complete and which one is not complete. So I will identify that there are 4 complete squares. But we also have to identify incomplete squares here, and I'll use the crosses to identify incomplete squares. There are these ones, there's a small one here, there's this, there's one here, here, one here, one here, there's this one, there's this one, there's this one, there is this one. So after identifying those ones, for us to be able to get the area of this particular field here, we are going to get the full squares, which are 1, 2, 3, 4. So there are 4 full squares plus a half of the incomplete squares. So half of the complete squares are 1, let me start from here or here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 incomplete squares. The reason why we are dividing by 2, or we are using only a half of this, is because the assumption is that one incomplete square plus another incomplete square will make one complete square. That assumption may not be true because this incomplete squares. Some of them are very small, some of them are very big. For example, if you take this one, this incomplete square plus this one, obviously is more than 1. But now we are said we are estimating, so that kind of argument will just be ignored. So if you have this one, we'll say this is 4 plus a half of 15 is 7.5. So we are going to say this is 11.5 centimeters squared. So this is the area on the paper. But like I said, you sometimes will find that you are given what we call the scale there. So if you are given the scale, remember this is the linear scale, we have to get the area scale factor. So the area scale factor out of this linear scale factor, we'll have to square this. After squaring it, it must be, this is 11.5 over x, assuming x now is the actual area. So we are going to say x here will be, because 1 times x will be 11.5 times 5,000 squared. That will be, if I try to multiply that, 5,000 squared times 11.5. That is 287,500,000 centimeters squared. So after getting centimeters squared here, it means therefore we can now divide or change it into meters squared or kilometers squared or hectares based on what the examiner wants from you. So that is basically what you do when you are dealing with the counting technique to estimate area of a particular region. And it's very basically easy, as you have seen. And if you want to find more about this, you can go back to book 1, or at least in book 4 also. At the beginning of area approximation, you'll find some area things there to do. Now, I want to bring you to new techniques that we are going to learn today. And there are new techniques that are much more technical, and we are going to try to make them as easy as possible. So the new techniques we are going to learn in this lesson are one of methods of approximating area. The first one will be the trapezium rule. The trapezium rule. And the second one will be the mid-ordinate rule. Mid-ordinate rule. These are the two rules we are going to learn in this particular chapter. And I will start with the trapezium rule. So today in our lesson we are going to learn about the trapezium rule. The trapezium rule. So we all of us know what a trapezium is. A trapezium is a regular shape which is kind of a piece of a rectangle over a square plus another triangle on it. That is what we call, or we are going to refer to, or what we know as a trapezium. So if I sketch a trapezium here, the name trapezium rule comes from the shape you already know. I believe these shapes you have done them in Form 2 mathematics class. So we are going to see, if I draw a shape like this one here is a trapezium. And I want to invite you to know that this rule is not going to be different from what you have learned before. And actually, if you know, remember, or you have to believe me when I say that in Form 4 chapters are actually not new chapters. They are actually a collection of some of the things, some of the ideas that we have learned in the course of your study from Form 1 to Form 3. So you realize that if we do this, we normally know that the parallel sides, we normally label them as A and B. That one I hope you remember. And the vertical, or the shortest distance between the two parallel lines is the height. So this is our height here. This is our height here. So we know that when we are getting the area of a trapezium, we normally say the area of a trapezium is a half h into A plus B. That is the area of the trapezium. And we are going to use this particular formula today a lot. And I want you to, I brought this idea here for us to be able to remember. Now, we want to really know what is the trapezium rule. What is really the trapezium rule? So let me wrap this one and be able to sketch for you something here so that we can really, trapezium is singular, but when I say trapezia, it means there are many, not more than one. So if you want to get 4 trapezia, you can actually see from here we have 1, 2, 3, 4. There, we have divided this. For remember that this one here must be uniform. This is going to be our H. So our H must be uniform because these are going to be the trapezia. A and B must be Y's. So this must be very uniform, and that's why we have to take equal sides. If I say 8 trapezia, we are going to take a half of this. So it means they are going to be kind of 1 trapezia will be here. Now, if I draw this trapezia, let me use dotted lines to be able to join these lines up here. This X here, they are there, and they are there. And I know sometimes there is a question people are asking, what about if we have said there are 4 trapezia, how did we reach there? Now the question will tell you to get the area under the curve between maybe x equals to 0 and x equals to 4, and x equals 4. Now, if you are told to give these particular values, the first value to appear will say, let that value be A. So we have A there, and the last value there will be B there. Now, the number of trapezia that we have been given, they said trapezia are 4. That is n equals to 4. So 4 is the number of trapezia that we need. Now, for you to get the height usually is given by B minus A. The last value of x you are told, and the first value of x, the smallest value of x, that is a, so b minus a divided by n. And in this case, our b is 4, our a is 0, divided by 4. So h here is 4 over 4, which is 1, meaning the value of h, the common height here, should always be 1 unit for each trapezia. Now, we have not got our trapezia yet, but you have drawn this thing. So what we have to do to get this trapezia, join one end of that, the other 2 parallel lines. The top ends of those 2 parallel lines, join each of them to the other. You'll find that you are forming shapes like trapezia, like I'm doing now. They may not be very visible, but if you join them, if you are keen, you may see something. So when you draw them like that, you realize that in these boxes here, the line we have drawn here is kind of above the trapezia. So this trapezia here will be overestimated. When you come here, probably you cannot tell because always the lines seem to be on the same line. Here also we are going to overestimate. Here we are also going to overestimate the area. So it means that overall the area under this curve will be overestimated. You can see that kind of view that we have there. Now that we have the h here, we know that this value here, we are going to label the first line. We know the a minus b for trapezia A. This is trapezia B, C, and D. We'll say that for trapezia A, this is y0, this is y1. You can start from y1. That's your decision as someone who's working. These are things that you are put to guide you. But once you understand what you're supposed to do, this one should not bother. You can put anything here, maybe even y negative 1, yn something. But we'll start with y0, y1, y2, y3, y4. You realize that if I started here with y1, I will have y5 on the other side. And sometimes people don't want y5 because we are dealing with 4 trapezia. Why do we then have y5? We just have to have the last number here should be equal to the number of trapezia we need to have. That's why we have to start with y0, what someone will call y0. Now we know that this down here, we have said the length that we have down here, we are going to refer to it as h. So we have h's all through. This is h, this is h, this is h, this is h, and we know the value of our h. Now, assuming we have to get the area of this shape under this curve between x equals to 0 and x equals to 4, we need to get the trapezia, the sum of the areas of all the 4 trapezia. And what we are going to do here is to get the area of trapezium 1 or trapezium A. And if I say area of trapezium A here will be, I gave the formula for a trapezium which is half h into A plus B. But remember now, a half h, we have our h, but A and B are not A and B anymore. A and B are now going to be the parallel lines, which is y0, y1 for the plus y1 for the trapezia A. For trapezia B, B is going to still be a half. Let me use this formula still. So this is the formula. Let me say this is the formula for trapezia. But now this is for area A. This for area B is going to be half h still. But now for area B, the two parallel lines are y1, y2. So y1 plus y2 here. For trapezia C is going to be still a half h into, but now our A and B are going to be y2 and y3. y2 plus y3. And then D is going to be a half h into y3 plus y4. I can just continue adding without checking because I know how numbers will really occur. Now we have got the areas of each of the 4 trapezia that we have, A, B, C, and D. Now for us to get the total area, we have to add the area of A plus the area of B plus the area of the C plus the area of D, which will just be A, total area here will be area of that A plus B plus C plus D. So when we add them, if I start by the A is a half h into y0 plus y1 plus B is a half h into y1 plus y2 plus area of C is a half h into y2 plus y3 plus that one of D is a half h into y3 plus y4. So viewers, what we are doing here is just to assemble, to bring these areas together, and by so doing we want to see something. Now we realize that in each of these formulas a half h is common. Half h, a half h, a half h, a half h. So we can actually factorize a half h out of all these things. By factorizing a half h, we are going to have a half h into y0 plus y1 for area 1 plus y1 plus y2 plus y2 plus y3 plus y3 plus y4. You realize that this one is for area A, this for area B, this for area C, this for area D, and the half h we have factorized out there. Now you realize that there's something unique from here to here. There's a repetition, y1, y1, y2, y2, y3, y3. But the ends, the first line and the last y are only singles. So again, we can do something here by saying this is a half h into y0 plus 2, because these things are 2, 2, 2, 2. 2, 2, 2. So we're going to say 2 into y1 plus y2 plus y3, then plus y4. So what we have done is simply to be able to factorize again here, because if I add y1 plus y1 is 2y1, y2 plus 2, y2, y2 plus y2 is 2y2, y3 plus y3 is 2y3. Again, now we factorize those twice, or let us see first. Someone may not actually see what we have done here. Let us see, y1 plus y1 will be 2, y1 plus y2 plus y2 will be 2, y2 plus y3 will be 3, y3, or 2y3, sorry, 2y3. So after that, we can then factorize 2. So we can say, let me remove this bracket here now. So this is, we have h into y naught plus 2, we now factorize 2 here. 2 into y1 plus y2 plus y3, close bracket, plus y4. So viewers, you see that now our rule is actually taking shape. If I come here to get some space so that we can now finalize, we'll say area under the curve now will be a half h into y naught plus 2 y1 y2 y3 plus y4. Then that, but let me use a different bracket here to show actually that these brackets are not the same, because there are two levels of bracket that we have here, the inner bracket and the outer bracket. Now viewers, this is the trapezium rule. Now in some cases you will find that this one is added to this one first, but that's now a choice. You can actually say now area will be a half h into y naught plus y4. These are actually the ends. These are actually the lines at the ends. They are always going to be single, but those one in the middle will be repeated because this area here shares y1. This B and C shares y2, C and D shares y3, so they have to be repeated. Then plus 2 into y1 plus y2 plus y3, close bracket, then you close there. So if you want to get this area, it means that first of all, we get h. And I've said, how do we get h? H is the same as b minus a over n, where n is the number of trapezes that you are needed to give. A is the first value of x you are told about, and b is the last one. Like in this case, we are told x0 to x equals to 4. So we actually got 4 minus 0 over 4 equals to 1. Then these values of h's, these values here, will be easier to obtain if you know the value of the function, assuming the function is y equals to x squared plus 4. Assuming that, if you have that particular curve there, then you can be able to substitute the values, corresponding values of x's here, to be able to get these values of y. You simply substitute and everything else. It means that if you have the function of the graph, you have the other details about between what range, what we call the limits. The limits where you should get the area of the domain, probably from x this to x that. You are able to calculate the area under a curve without actually even drawing this area. Now, if you have many values of y, so it means that the general mid-ordinate rule will be area equals to a half h into y naught plus yn, where n could actually be unknown, plus 2 into y1, y2, y3, plus, we don't know what is there, to yn minus 1. This actually will give you the values y. Now sometimes I don't like using n here because students will be struggling to understand. This first formula will actually help you, so that if you have y1 to y6, y0 to y6, then you expect that y0 and y6 will be the one here. Then between y1 to y5, you are going to have them here times 2. Then probably the problem is solved. So this is the trapezium rule that we are going to use now to be able to try a few questions that we are going to meet. And the first example here is going to be an example dealing with a curve. We are told area is bounded by up to 4 things, you realize this line is the curve. We are told bounded by the curve, so this part of the curve is here. The line x is 1 is here. The line x is 5 is here. The x-axis is here. So we need this region here. And like I said, we need to find this area. Remember, the question has not told us to be able to use how many trapezia. We can use like 1, 2, 3, 4. We can divide this thing into 4, or we can divide it into 8 parts. Now remember that the more the trapezia, the more accurate the area. The more accurate the area will be. So let's try to be able to calculate with 4 trapezia first, assuming we are using n equals to 4. So if n equals to 4, let me divide this thing this way. Here is this way. Remember, this one is a part where you have a graph sketch for you. So you can actually see what you are dealing with. Now, mostly I like using a table because I know I'm going to have this y. The first y is not here because we are dealing with y equals to 1. So the y naught is here. This is y1. This is y2. This is y3. This is y4. Remember, we are using 4 trapezia. We are using 4 trapezia. So the first thing I want to do is to draw a table. From this table, we are going to fill in these values of y's. And we know a table of x and y. So this is x, this is y. 1, 2, 3, 4. So once I have that, x1, I'll start with that because that's the first y. So x1, x2, the second y is there, x3, and x4 there. The y's, this will be my y naught, y1. Oh, we have left something is missing here. So y2, y3, y4. So what we are going to do here is to just use a calculator to find if we are using this curve, what's the value of this particular y naught here when x is 1. We substitute the value of x here. When x is 1, what will be y? So when x is 1, we'll say a half into 1 squared plus 5. That is 5.5. So this first y will be 5.5. What about if it is 2? That is 2 squared plus 5. It's going to be 7.0. What about if it is 3? So 3 squared plus 5 is going to be 9.5. What about if it is 4? It's going to be a half times 4 squared plus 5 is 13.0. What about if it is 5? So it is going to be 5 squared plus 5 is 17.5. So we have filled the values of y. Remember, in our formula, we needed just y's. And because we have 4 trapezia here, we just need to have the formula area equals to half h into y naught, like I said, plus y 4 in this case, close bracket, let me have a bigger bracket here, plus 2 into y1 plus y2 plus y3 in a close bracket. Now let us substitute. Our y naught is 5.5, but let's find h first. H, we said h equals to b minus a over n, where n is the number of trapezia, and we have said in this case we are using 4 trapezia. And our a is 1, our b is 5. So we'll say h equals to b5 minus 1 over 4. This is 4 over 4, which is 1. So we have 1 unit as the height. So we'll say this is a half times 1 in bracket. Y naught is 5.5 plus y4 is 17.5 plus 2 into y1 is 7 plus 9.5 plus 13. So we have that. The next thing that remains is for us simply to do the math, which is 5.5 plus 17.5. That is, we are going to have a half. Half times 1 is a half. In bracket 23 plus. We have 7. 7 plus 9.5 plus 13 is 29.5 times 2. Sorry. So it's 29.5 times 2. That is 59. So you have 59 here. So you have a half times 59 plus 23 is 82. 82. So if you have 82 times a half, you get 41. So the approximate area, square units, approximate area of this particular region, region bound by the line x is 1, x is 4, x is 5, sorry, the curve y equals to half x squared plus 5, the x-axis is actually going to be approximately, not exactly, but approximately 41 square units. That is an example of how to deal with trapezium rule, which is sketched for you. Let us also go to example 2, which is going to deal with an area which is actually not sketched. So you are just asked to be able to work it out. Okay, now let's look at example 2 that deals with the area of the curve. We are told to estimate the area enclosed by the curve y equals to half x squared plus 1, x equals to negative 3, x equals 3, and x-axis using 6 trapezia. Now, we don't need to sketch the curve. As I can see, the curve is not on the negative side of the x-axis, it's on the upper side, so we don't need to sketch anything or maybe to see how the graph will be, because probably it is something kind of a trough. So we just need to sketch this one. We know that here, if you have 6 trapezia, and we are moving from x equals to negative 3 to x equals 3, we can get the value of h, and I said that h equals to a or b minus a over n, where n is actually the number of trapezia. So b in this case is 3 minus a, which is negative 3, divided by 6. So h here equals to 6 over 6, because negative followed by negative, or negative minus times negative is positive. This is 1. So the height is 1 unit. Now we know that we have up to 6 trapezia. So if you have 6 trapezia, I should have from y0 to y6. From y0 to y6. And how do I get this y's? If I have to get y0, the x value of y0 should actually be the first value of x, which is negative 3. What about y1? The first value of y1 should be y0 plus h. y0 plus h. Now h is the common height. So y0 here is negative 3. So I'll say negative 3 here plus 1, which is the height, will give us negative 2. So y1 is negative 2. y2 will also be y0, which we now know is negative 3, plus 2h, 2 times the common height, where the common height now is 1. So if you multiply 2 times 1, you get 2, plus negative 3, you get negative 1. So you do like that. The y2 will be y0 plus 3h, like that, until you reach y6. So we are going to see that here. As that happens, this is x, this is y, and this is negative 3, negative 2, This is what we are doing. You see negative 3, why not? X value at that one negative 2, X value at y2 will negative 1, and you can already go like that because now you know the trend. It's a difference of plus 1. So add 1 here is going to be 0. Add 1 to 0 is 1. Add 1 to 1 is 2. Add 1 to 2 is 3. So we have the y values which will give us 1, 2, 3, 4, 5, 6, 7. 7 because we have y naught. So we have y naught, then y1 to y6, those are 6 plus y naught is 7. So this will be our y naught, y1, y2, y3, y4, y5, y6. So if we have that, what do we do here? We now use a calculator to be able to fill in the values of y corresponding to the values of x in the table. And there are our curve is here, so we are going to estimate negative 3. So half times negative 3 squared plus 1. That is 5.5, positive 5.5. Then we are going to get a half times negative 2 squared plus 1. That is 3. Then we are going to get a half times negative 1 squared plus 1. That is 1.5. Then we are going to have 0, a half into 0 squared plus 1. We'll get 1.0. Then we are going to have 0.5 or a half into 1 squared plus 1 is 1.5. And you realize they'll repeat like that. 0.5 into 2 squared plus 1 is 3.0. And finally, 0.5 into 3 squared plus 1 is 5.5. So we have the values of y. We can now go with the formula to get our area, and the area we said is a half h according to the trapezium rule into y naught, in this case the last figure, and the first and the last, plus y6 plus 2 into the ends y is naught, y6, then you have to bring in y1 to y5. So y1, y2, y3, y4, y5. So let's just substitute a half h, and h we already got h to be 1, so we'll take 1 here, times into y naught is 5.5 plus y6 is 5.5 plus 2 into y1 is 3 plus 1.5 plus 1.0 plus 1.5 plus 3.0. We close the bracket down. So let's go. Half times 1 is a half times 5.5 should be plus 5.5 is 11 times 2 is 11 plus 2 into 3 plus 3 plus 1.5 plus 1.5 plus 1 is 10. So 10 there. So we are going to have a half into 11 plus 20. This is going to be a half times 31. So half times 31, a half times 31 is 15.5. 15.5 square units. 15.5 square units. We are not going saying 15 centimeters, 5.5 centimeters squared because we actually do not know the units with which this one was measured. So we are just going to say 15 square units, whichever units used. They could be meters, they could be centimeters, they could be kilometers. We don't want to really know about that. But from now we can be able to know how to really estimate the area under the curve without actually depending on a graph. But sometimes the question may force you to be able to deal with some of this. You can be given a question without the limits here, the boundaries on the x-axis, then you are forced to be able to look for that. So viewers, that is the end of our lesson on trapezium rule. Let's see you next time when we are looking at the mid-ordinate rule. Thank you very much, and please do not forget to subscribe to our channel so that you can support us in this endeavor of making lessons and be able to teach the community at this time of coronavirus.